Hello learners, we have learned about Gibbs phase rule in the context of metamorphic rocks, and today we will talk about composition space. This is because we define metamorphic rocks in terms of chemical system, and if it is a closed chemical system, the transformation of system components into various proportions of phase component represents composition space. Just to recall, there were system components as SiO2, Al2O3, CaO, MgO and more, and phase components which actually describe the chemical variability of phases. This is because minerals as phases are normally impure phases, that is, their composition is not fixed. There are very few minerals whose composition is fixed. Quartz represents one of those, and to an extent the aluminosilicates also represent more or less pure phases, but most other phases are impure phases. There are also phase components. Now, if we were to look at one component system as we saw in the Gibbs phase rule, the rocks are more complex than that. So, we will study 2 component and 3 component system, and we will also like to see whether we can do a reduction of the dimension to represent the composition space in a simpler way. Let us look at a 2 component system. A 2 component natural system here is that of SiO2 and MgO as the 2 system components. Now, in this system components, in this diagram, the horizontal axis is represented by SiO2 and NSiO2, this is N1, this is N2, that is number of moles of SiO2, and on the vertical axis this is MgO and N1 and N2. Now, these system components also represents 2 phases, that is quartz and periclase. So, these are the 2 minerals which are present in this system. Besides these, there are other phases which also are made up of by a combination of these 2 system components. One of the common phase is N-statite. N-statite is 1 MgO and 1 SiO2. When we combine that, it becomes MgSiO3, that has an equal proportion of SiO2 and MgO. And phosphorite, which has 2 magnesium oxide and 1 silicon dioxide. So, if we combine 2 MgO and 1 SiO2, it becomes Mg2SiO4. In the normal plots using Cartesian coordinates and these number of moles as coefficients, we can plot quartz here and periclase here, and for plotting N-statite we will draw one line from SiO2 going up and one line from NMgO1, and their intersection will give us a point which will have 1 MgO and 1 SiO2. Similarly, if we were to plot phosphorite, which is an olivine, that will have 2 MgO. So, we draw a horizontal line of 2 MgO and a vertical line of 1 SiO2. Their intersection will give us Mg2SiO4. This diagram is actually a two-dimensional composition diagram in which 2 component system is represented in terms of various phases. To reduce one dimension of this and to represent it in a linear, not in area but in a linear fashion, we can adopt or do one thing, that is, we can project all the phases on a 1 mole line. So, in this second diagram, we have joined 1 mole MgO to 1 mole SiO2. So, this diagonal line represents that particular 1 mole proportion of both of these system components. Onto that we have projected the various phases, that is SiO2 remains there because it does not change. So, this end is SiO2 of quartz. At 1/2 of this line representing equal proportion of MgO and SiO2 is ancetite, which is represented by the intersection of this line with the Cartesian coordinate line, and at 2/3 of MgO and 1/3 of SiO2 it represents forsterite. So, now this one line itself can represent the 4 phases in proportions which represent these minerals. To arrive at the coordinate for this line, we have a formula, that is coordinate of any phase like ancetite, that is A dash, is equal to the number of moles of SiO2 divided by the sum of the 2 components, comma the number of moles of MgO divided by the sum of the 2 components. In this case it is 1 by 1 plus 1. So, it will be 0.5, 1 by 1 plus 1, 0.5. Therefore, this ancetite will plot here. For forsterite it will be 1 by 1, that is SiO2 plus 2 MgO. So, 1 by 3, and this will be 2 MgO by 1 plus 2, that is 3. So, it will be 1 by 3 comma 2 by 3, and therefore, it will plot here. So, this is one way of reducing the number of dimension, and these coordinates arrived at in this fashion are called as barycentric coordinates. The components can be, both system and phase components can be expressed either as oxide units or as atom units or as cation units or as oxygen units. So, any way they can be expressed, there is total independence of that. But when we look at a rock, we see that there are at least 10 major oxides that mostly define any rock, and because a metamorphic rock is transformation of a pre-existing rock or a protolith. So, therefore, those same components, if it is an isochemical transformation, will be there. What are these components? These can be SiO2, Al2O3, TiO2, chromium oxide, iron oxide, ferric iron oxide, manganese oxide, magnesium oxide, calcium oxide, and others. But if we try to draw a plot of Cartesian coordinate or barycentric coordinates of 10 components, it becomes too complex, and therefore, we need to reduce. There is also an interesting fact that in most of the metamorphic rocks, the number of minerals present are 3, 4, 5 or 6, which means that even though the major components may be larger number, the rocks behave as if it is made up of smaller number of components. So, there is a justification for reducing the number of components of the rocks. Now, if we are able to reduce it to 3 components, it provides us a 2-dimensional view. Now, supposing these 3 components are X, Y and Z, and there is a mineral which contains equal amount of X and Y, then that mineral will plot at the center of X and Y line. If it does not contain any Z, then it will plot on X and Y line. However, if it is made up of equal number of X, Y and Z, then it will not plot on any of the peripheral lines, but it will plot in the center. Similarly, a YZ equal amount mineral will plot here. A mineral which contains no Y, but is made up of 2 times Z and 1 times X will plot on XZ line at this point. So, in proportions of these, we can conceive of similarly the other minerals to be projected and presented, the examples of which we will see shortly. When these minerals are present in such a manner that they represent good smooth grain boundary context, we say that they are in equilibrium. And if they coexist, the phases coexist, we join them. For example, in a XYZ component rock, if two minerals made up of XY and XYZ occur in good textural situation, we can join them by a line, and these lines which join coexisting phases are called as tie lines. We will see its utility in a much greater way shortly with actual examples. So, the tie lines denote coexisting phases, and by coexisting means that mutually in equilibrium. Within three component diagram, a tie line represents two phase field and a triangular area represents three phase field. Similarly, each such diagram represents a snapshot of a range of pressure and temperature condition. How? You see that if it is a three component diagram, that is x, y and z, and a subfield of a triangular diagram is there, that will represent an area. Now, in a three component diagram, if we recall the Gibbs phase rule, P plus F is equal to 2 plus C. If in a three component diagram three phases coexist, that means the degree of freedom is 2. If the degree of freedom is expressed by pressure and temperature, then a triangular space will represent a range of pressure and temperature. And the evolution of metamorphic rocks is tracked by looking at how the arrangement of tie lines change from one set of diagram to the other set of diagram. The arrangement of tie lines is called as topology of phase diagram. So, these are phase diagrams. Now, let us look at some actual example of such rocks where we are displaying the composition space and its changes. First, let us consider not all types of rocks. We will look at one subset of rocks. One of the common subset of igneous rocks is basalts. Basalts represents those rocks which contain significant amount of calcium, silicon, aluminum, iron, magnesium, and contains very less potassium. Now, if we are looking at those and we are able to reduce the components to 3, then we are not actually representing the true components. We have reduced those 8, 10 components to 3, which means that these 3 are now pseudo components. So, these are not only phase diagrams, these are also called as pseudo component diagrams. In arriving at pseudo component diagram for basalt, in reducing component, what we do is that we do not consider SiO2 as one of the component. The reason is that, as I explained earlier, silicon dioxide as quartz is one of the rare pure phase. So, if quartz is present containing SiO2 as a phase, then that is not going to change in composition even if it is present from low grade transform basalt to high grade transform basalt. So, we will consider that quartz is always present. So, when the system components are readjusting into phase components, the other that like aluminum oxide, calcium oxide, iron, magnesium, they are participating and they are representing the phase changes. So, if we keep SiO2 aside, we are left with major components like Al2O3, CaO, FeO, MgO, Na2O, K2O. In further order to reduce, we combine FeO and MgO. Why? Because iron magnesium ions have properties very similar to each other in terms of ionic radii and charge. So, they substitute for each other and they can be combined, though we will lose some information, but the combination allows us to reduce one more component. So, besides Al2O3 we require FeO and MgO. Now, since potassium and sodium are relatively much less in basaltic rocks, we will not consider them for the moment. So, we are left with Al2O3, FeO plus MgO and calcium oxide as three possible pseudo components to represent the system composition of basalt. So, we will now look at how do we reduce these system components into pseudo components. For A, which represents Al2O3, we make it equal to Al2O3 and add ferric iron. Why do we add ferric iron? Because the trivalent aluminum and ferric iron substitute each other, and therefore we combine these two and we substitute Na2O and K2O, 1 mole of Na2O and 1 mole of K2O. Why do we do this? Is because since we are not considering the sodium part of the plagioclase and the potassium present in basalt if it is there, we presume that sodium and potassium are associated with the feldspars only. If we recall the formula of sodium and potassium feldspar, it is NaAlSi3O8 or KAlSi3O8, which has 1 mole of Na2O for each mole of Al2O3. So, therefore, if sodium is present and is associated with the plagioclase feldspar, the amount of aluminum which will be available to be shown in these pseudo component diagram will have to be reduced by the amount which is associated with plagioclase. Since that is in 1:1 proportion, so we subtract from Al2O3 the Na2O and K2O. So, this gives us a pseudo component. For C, we have CaO, but if a mineral contains some amount of phosphate or P2O5, then apatite is an early formed calcium bearing mineral, and the amount of calcium in apatite is 3.3 times that of P2O5. So, that much of calcium must have been not available to be reflected in these diagrams. So, we have to reduce that CaO minus 3.3 P2O5 to make C component, and for F we combine FeO and MgO, and if MnO is also present in significant amount, since it has similar properties in terms of the exchange capability, so that also is made together. So, now we have three pseudo component A, C and F. We will see now how and where these various minerals are plotted in this diagram. So, this is an ACF diagram where many minerals are plotted. We will actually see plot of one mineral or two minerals shortly. Now, you see that in AC line, for example, at midway anorthite, lawsonite and lawmontite, three minerals are plotted in this diagram. The minerals which are plotted in between represent presence of A, C and F, all three components. The minerals which are present on lines show that one of the component is not present. The mineral which are present on points like andalusite, kyanite, sillimanite, they represent that the other two pseudo components are not present in them. Let us look at actual plotting of one or two minerals. For example, here you see a triangular ACF diagram. In this ACF diagram, let us plot pyroxene and plagioclase. The formula of pyroxene is CaMgSi2O6. If we break this down in terms of the components which we are using as system and phase components, that is oxides, then it gets broken down into 1 CaO, 1 MgO and 2 SiO2. Since SiO2 we are not considering in this diagram, now we will calculate the plotting position of diapside. For that we will say A is equal to 0, because in this mineral there is no Al2O3. So, A will be 0, which means that it will be plotted on CF line. Now, it contains 1 CaO and 1 MgO. For the coordinate plotting, we will do C is equal to C divided by A plus C plus F. C divided by A plus C plus F. C is 1 divided by A is 0, C is 1 and F is 1. So, 1 by 2. The value of C has come as 1 by 2. Similarly, value of F, which is represented here by MgO, will also be MgO divided by CaO plus MgO plus Al2O3, that is 1 by 2. So, that means for both C and F values are half and there is no A in this. So, that it will plot midway between C and F, that is the plotting position of diapside. Let us look at anorthite, which the formula is CaAl2Si2O8, and if we break down formula in the similar fashion, it has 1 CaO and 1 Al2O3 and no F component, that is FeO-MgO. So, therefore, it will plot on AC line, which has F0. And in the fashion similar, when we calculate the value of C component, it is C, that is 1 divided by 0 plus 1 plus 1, that is half, and anorthite also gets plotted on midway. This way we can plot any number of minerals with actual compositions. If we find in a rock that quartz, anorthite, that is quartz, plagioclase and pyroxene occur together in textural equilibrium, we will join these two and that will represent the quartz, plagioclase, pyroxene tie line. In this figure now, you see that the rock contains, these are garnets, there are some orthopyroxenes here and hornblende, that is a calcic amphibole which is present. So, they are all present together and we have plotted plagioclase position, clinopyroxene position and garnet position, and this triangular area represents the space shown by this composition. Let us discuss why we are using this diagram and the utility. Supposing in a metamorphic terrain, there are different assemblages present. In an ACF diagram, let us consider 3 assemblages. One assemblage is garnet, clinopyroxene, quartz and plagioclase. If we plot the positions of plagioclase, clinopyroxene and garnet, then that will be represented by a triangular area in this. Remember, quartz is always present. So, quartz is not plotted, but is present here. So, this triangle marked by letter 1 represents assemblage 1. There is another assemblage, that is assemblage number 2, which is calcite, plagioclase and clinopyroxene. So, calcite gets plotted here, clinopyroxene is here and plagioclase is here. So, the assemblage 2 gets plotted here. In plotting assemblage 1 and 2, the topology of the ACF diagram does not get disturbed. So, therefore, the 3-phase assemblage 1 and 3-phase assemblage 2 both can coexist with each other, which means that both can coexist within the same range of 2 degree of freedom represented by pressure and temperature, and they are called as compatible assemblages. There is no other way other than this kind of phase diagram to know whether the assemblages are compatible or not. Now, let us examine the third assemblage, which is calcite, garnet, clinopyroxene and quartz. So, that rock, when we try to plot calcite here, garnet here, clinopyroxene here, this triangle when we try to plot, we find that the plagioclase clinopyroxene tie line is crossed. This is not permitted, that is, if there is a crossing of tie line, remember tie line represents coexisting minerals. If there is a crossing of tie line, that means there is a reaction. That tells us that there is a reaction isograde, and this diagram also allows us to know what that reaction is. One tie line is getting crossed by other. So, one side will be reactant, the other side will be product. Say for example, calcite garnet is here and the other tie line is plagioclase CPX. So, therefore, the use of these kind of diagram allow us to tell that there is a reaction isograde present which cannot be interpreted by any other way. If we now look at the way these diagrams are shown, they are pseudo component diagram, they are phase diagram because they are representing phases, they are chemographic diagram because they are representing for a system the phase composition changes, and they are also compatibility diagram because they are able to distinguish which of the assemblages are compatible and which of the assemblages are not compatible. And this is possible only with this kind of diagram. So, therefore, there are 4 titles, but they represent only one diagram, and this kind of composition space analysis is the only way by which we can pick the reaction isogrades. Actually, you see that the phase diagrams, pseudo component diagram, compatibility diagrams and the chemographic diagrams are so useful for interpreting the mineral assemblages and metamorphic rocks. In the next program, we will learn about use of these diagrams for metabolitic rocks. Thank you, learners.